4. Refraction of light at plane surfaces. B. Light. Syllabus. First, refraction of light through a glass block and a triangular prism. Qualitative treatment of simple applications such as real and apparent depth of objects in water and apparent bending of sticks in water. Application of refraction of light. Scope of syllabus. Partial reflection and refraction due to change in medium. Laws of refraction. The effect of speed v, wavelength lambda, and frequency f due to refraction of light. Conditions for a light ray to pass undeviated. Values of speed of light c in vacuum, air, water, and glass. Refractive index mu is equal to c upon v. V is equal to f lambda. Value of mu for common substances such as water, glass, and diamond. Experimental verification. Refraction through glass block. Lateral displacement. Multiple images in thick glass plate or mirror. Refraction through a glass prism. Simple applications. Real and apparent depths of object in water. Apparent bending of a stick underwater. Simple numerical problems and approximate ray diagrams required. Second, total internal reflection. Critical angle. Examples in triangular glass prisms. Comparison with reflection from a plane mirror. Qualitative only. Application of total internal reflection. Scope of syllabus. Transmission of light from a denser medium, glass or water, to a rarer medium, air, at different angles of incidence. Critical angle C, mu is equal to 1 upon sine C. Essential conditions for total internal reflection. Total internal reflection in a triangular glass prism. Ray diagram. Different cases. Angles of prism 60 degree, 60 degree, 60 degree, 60 degree, 30 degree, 90 degree, 45 degree, 45 degrees, 90 degrees. Use of right angle prism to obtain delta is equal to 90 degrees and 180 degrees. Ray diagram. Comparison of total internal reflection from a prism and reflection from a plane mirror. A. Refraction, laws of refraction, and refractive index. In class 9th, we have read the reflection of light from the plane and spherical mirrors. The return of light in the same medium after striking a surface is called reflection of light. The reflection of light rays obeys two laws. First, the angle of reflection is equal to the angle of incidence. And second, the incident ray, the normal at the point of incidence, and the reflected ray all lie in one plane. Here we shall study the refraction of light through the plane and spherical surfaces of transparent media. Light has the maximum speed is equal to 3 into 10 raised to 8 meter per second in vacuum, and it travels with different speeds in different media. It travels faster in air than in water or in glass. The speed of light is 3 into 10 raised to 8 meter per second in air, 2.25 into 10 raised to 8 meter per second in water, and 2 into 10 raised to 8 meter per second in glass. The speed of light remains constant in a transparent homogeneous medium. While passing from one medium to the other, if light slows down, the second medium is said to be optically denser than the first medium, and if light speeds up, the second medium is said to be optically rarer than the first medium. Thus, water and glass are optically denser than air, or air is optically rarer than water and glass. Similarly, glass is optically denser than water, or water is optically rarer than glass. Action of light. Partial reflection and refraction at the boundary of two different medium. In a transparent medium, although light travels in a straight line path, but when a ray of light traveling in one transparent medium strikes obliquely at the surface of another transparent medium, a part of light goes back to the same medium, obeying the laws of reflection, and is called the reflected light. The remaining part of light enters into the other medium and travels in a straight path different from its initial direction and is called the refracted light. Thus, at the boundary separating the two media, light suffers a partial reflection and partial refraction. Thus, the change in direction of the path of light when it passes from one transparent medium to another transparent medium is called refraction. The refraction of light is essentially a surface phenomena. In figure, S' is the surface separating the two media, say air and glass. When light traveling in one medium falls on the surface S', a small part of it is reflected back in the same medium, obeying the laws of reflection, and the rest of it is refracted through the other medium. That is, there is a partial reflection and partial refraction at the boundary surface. The intensity or the amplitude of the refracted light will obviously be less than that of the incident light because a part of the incident light has suffered reflection. In figures, for the incident ray AO, the refracted ray is OB, the reflected ray is OC, and the normal at the point of incidence O is NOM. The angle of incidence I is angle AON, and the angle of refraction R is angle BOM. Note that the angle R is not equal to the angle I, that is, OB is not in direction of OA. Observations. It has been experimentally observed that 1. When a ray of light travels from a rarer medium to a denser medium, say from air to glass, it bends towards the normal, that is angle R is less than angle I, as shown in figure. The deviation of the ray from its initial path is delta is equal to I minus R. 2. When a ray of light travels from a denser medium to a rarer medium, say from glass to air, it bends away from the normal, that is angle R is greater than angle I, as shown in figure. The deviation of the ray is then delta is equal to R minus I. 3. The ray of light incident normally on the surface separating the two media passes undeviated, that is, such a ray suffers no bending at the surface. Thus, if angle of incidence, angle I, is equal to 0 degrees, then angle of refraction, angle R, is equal to 0 degrees, as shown in figure. The deviation of the ray is 0, that is, delta is equal to 0 degrees. Note, in discussing refraction now onwards, the reflected ray from the boundary surface will not be shown, although it is always there. Let us now see cause of refraction or cause of change in direction. When a ray of light passes from one medium to another medium, its direction or path changes because of the change in speed of light in going from one medium to another. In passing from one medium to other, if light slows down, it bends towards the normal, and if light speeds up, it bends away from the normal. If the speed of light remains same in passing from one medium to another, the ray of light does not bend. It passes undeviated. Note, for normal incidence, angle I is equal to 0 degree. The speed of light changes, but the direction of light does not change. Of refraction. The refraction of light obeys two laws of refraction which were given by the Dutch scientist Wilbord Snell, so they are known as Snell's laws after his name. They are 1. The incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane. 2. The ratio of the sine of the angle of incidence I to the sine of the angle of refraction R is constant for the pair of given media. That is, mathematically, sine I upon sine R is equal to constant mu 2 1. Let this be equation 1. The constant mu 2 1 is called the refractive index of the second medium with respect to the first medium. Here, the Greek letter mu is the symbol used for refractive index. Effect on speed v, wavelength lambda, and frequency f due to refraction of light. 1. When a ray of light gets refracted from a rarer to a denser medium, the speed of light decreases. When it is refracted from a denser to a rarer medium, the speed of light increases. 2. The frequency of light depends on the source of light, so it does not change on refraction. 3. The speed of light v in a medium, the wavelength of light lambda in that medium, and the frequency of light f are related as v is equal to f lambda, or frequency f is equal to v upon lambda. Let this be equation 2. When light passes from a rarer to a denser medium, the wavelength decreases, since speed of light decreases, but its frequency remains unchanged. When light passes from a denser medium to a rarer medium, the speed of light increases, and hence its wavelength increases. Refractive index. The refractive index of second medium with respect to the first medium is defined as the ratio of the sine of the angle of incidence in the first medium to the sine of the angle of refraction in the second medium. Unit. The refractive index has no unit as it is the ratio of two similar quantities of light in different media. Relationship between refractive index and speed of light. Mu is equal to C upon V. The speed of light is maximum in vacuum and is equal to 3 into 10 raised to 8 meter per second. The speed of light in air is nearly same as in vacuum. It is denoted by the symbol C. In any other transparent media, the speed of light is less than that in air or vacuum. The refractive index of a medium is generally defined with respect to vacuum or air and is called the absolute refractive index or simply the refractive index of the medium. It is denoted by the letter mu. The refractive index of a medium is defined as the ratio of the speed of light in vacuum or air to the speed of light in that medium. That is, refractive index or mu is equal to speed of light in vacuum or air, C, upon speed of light in that medium, V. Examples. 1. The speed of light in air is 3 into 10 raised to 8 meter per second, and in glass it is 2 into 10 raised to 8 meter per second. Therefore, the refractive index of glass is 3 into 10 raised to 8 upon 2 into 10 raised to 8, which equals 1.5. 2. The speed of light in water is 2.25 into 10 raised to 8 meter per second. So, refractive index of water is equal to 3 into 10 raised to 8 upon 2.25 into 10 raised to 8, which equals 4 upon 3, which is equal to 1.33. 3. The refractive index of diamond is 2.41. It means that light travels in air 2.41 times faster than in diamond. Since the speed of light in air is 3 into 10 raised to 8 meter per second, the speed of light in diamond is 1.245 into 10 raised to 8 meter per second. In general, the refractive index of second medium with respect to first medium is related to the speed of light in the two media as follows. Mu21 is equal to speed of light in medium 1 upon speed of light in medium 2. Let this be equation 4, where mu21 represents the refractive index of medium 2 with respect to medium 1. If V1 is the speed of light in medium 1 and V2 is the speed of light in medium 2, then from equation 3, mu21 is equal to V1 upon V2, which equals C upon V2 upon C upon V1, which equals mu2 upon mu1. Let this be equation 5. Here, mu1 and mu2 are the absolute refractive indices of the medium 1 and 2 respectively. Note, if the refractive indices of medium 1 and medium 2 are same, the speed of light will be same in both the media. So a ray of light will pass from medium 1 to medium 2 without any change in its path, even when the angle of incidence in medium 1 is not 0. Refractive index of some common transparent substances. Refractive index mu of some common substances. Vacuum 1, air 1, or 1.0003, ice 1.31, water 1.33, methylated spirit 1.36, ether 1.36, alcohol 1.37, kerosene 1.41, sulfuric acid 1.43, paraffin oil 1.44, glycerine 1.47, turpentine oil 1.47, ordinary glass 1.5, crown glass 1.53, quartz 1.54, rock salt 1.56, carbon disulfide 1.63, flint glass 1.65, ruby 1.76, diamond 2.41. Examples 1. Refractive index of glass with respect to water is equal to speed of light in water upon speed of light in glass, which equals 2.25 into 10 raised to 8 upon 2.0 into 10 raised to 8, which equals 1.125. Or refractive index of glass with respect to water is equal to refractive index of glass upon refractive index of water, which equals 3 by 2 upon 4 by 3, which further equals 9 upon 8, which equals 1.125. Refractive index of water with respect to glass is refractive index of water with respect to glass is equal to speed of light in glass upon speed of light in water, which equals 2.0 into 10 raised to 8 upon 2.25 into 10 raised to 8, which equals 0.89. Or refractive index of water with respect to glass is equal to refractive index of water upon refractive index of glass, is equal to 4 by 3 upon 3 by 2, which equals 8 by 9, which further equals 0.89. Examples. 1. The speed of light in air is 3 into 10 raised to 8 meter per second, and in glass it is 2 into 10 raised to 8 meter per second. Therefore, the refractive index of glass is 3 into 10 raised to 8 upon 2 into 10 raised to 8, which equals 1.5. 2. The speed of light in water is 2.25 into 10 raised to 8 meter per second. So, refractive index of water is equal to 3 into 10. Relationship between wavelength in the two medium. If a ray of light of frequency f and wavelength lambda suffers refraction from air, speed of light is equal to c. To a medium in which the speed of light is v, then the frequency of light in the medium remains unchanged, equal to f, but the wavelength of light changes to lambda dash, such that in air, f is equal to c upon lambda, and in the medium, f is equal to v upon lambda dash. Therefore, c upon lambda is equal to v upon lambda dash, or lambda dash is equal to v upon c lambda. But c upon v is equal to mu, the refractive index of the medium. Therefore, lambda dash is equal to lambda upon mu. Let this be equation 6. Obviously, when light passes from a rarer to a denser medium, mu is greater than 1. Its wavelength decreases, lambda dash is less than lambda. But if light passes from a denser to a rarer medium, mu is less than 1, its wavelength increases, lambda dash is greater than lambda. Factors affecting the refractive index of a medium. The refractive index of a medium depends on the following 3 factors. 1. Nature of the medium, that is its optical density. As smaller the speed of light in a medium relative to air, higher is the refractive index of that medium. For example, V glass is equal to 2 into 10 raised to 8 meter per second. Mu glass is equal to 1.5 and V water is equal to 2.25 into 10 raised to 8 meter per second. Mu water is equal to 1.33. 2. Physical conditions such as temperature. With increase in temperature, the speed of light in medium increases, so the refractive index of medium decreases. 3. The color or wavelength of light. The speed of light of all colors is same in air or vacuum, but in all other transparent medium, the speed of light is different for different colors. In a given medium, the speed of red light is maximum and that of violet light is least. Therefore, the refractive index of that medium is maximum for violet light and least for red light. That is, mu V is greater than mu R. The wavelength of visible light increases from the violet to the red end, so refractive index of a medium decreases with the increase in wavelength. Principle of reversibility of the path of light. According to this principle, the path of a light ray is reversible. In figure, a ray of light AO is incident at an angle I on a plane surface S' separating the two media 1 and 2. It is refracted along OB at an angle of refraction R. The refractive index of medium 2 with respect to medium 1 is equal to sine I upon sine R. Now, if the refraction takes place from the medium 2 to 1, the principle of reversibility requires that the ray of light incident along BO at O at an angle of incidence R in medium 2 will get refracted only along OA at an angle of refraction I in medium 1 and in no other direction than OA. The refractive index of medium 1 with respect to medium 2 is then refractive index of medium 1 with respect to medium 2 is equal to sine R upon sine I. From equations first and second, mu21 into mu12 is equal to sine I upon sine R into sine R upon sine I, or mu21 into mu12 is equal to 1. Let this be equation 7. Or mu12 is equal to 1 by mu21, or mu21 is equal to 1 by mu12. Let this be equation 8. Thus, if refractive index of glass with respect to air is mu Ga is equal to 3 by 2, the refractive index of air with respect to glass will be mu Ag is equal to 1 by 3 by 2, which equals 2 by 3. Experimental verification of laws of refraction and determination of refractive index of glass. Procedure 1. Place a rectangular glass block on a white sheet of paper fixed on a drawing board and draw its boundary line PQRS with a pencil as shown in figure. 2. Remove the block and on the boundary line PQ, take a point O nearly at its middle and then draw a normal NOM on the line PQ at the point O. 3. Draw a line AO inclined at an angle I, say 40 degrees, to the normal NOM. 4. Replace the block exactly on its boundary line. 5. Fix two pins A and B vertically on the board about 5 centimeters apart on the line AO. 6. Now looking from the other side RS of the block by keeping the eye close to the plane of the board, fix two more pins C and D such that the base of all the 4 pins A, B, C and D appears to be in a straight line as seen through the block. 7. Then remove the pins one by one and mark dots at the position of each pin with a fine pencil. Remove the block and join the points C and D by a line BC to meet the boundary line RS at a point B. Join the points O and B by a straight line, which gives the path of light ray inside the glass block. Here AO represents the incident ray, OB the refracted ray through the block, and BC the emergent ray. NOM is the normal at the point of incidence O. Angle AON is the angle of incidence I, and angle BOM is the angle of refraction R. 8. Measure the angles I and R. Read the values of sine I and sine R from the sine table and calculate the ratio sine I upon sine R. This ratio is constant and it gives the refractive index of glass. Alternative method. In order to verify the law of refraction without measuring the angles I and R, draw a circle of suitable radius with a point O as center, which intersects the incident ray AO at D and the refracted ray OB at E. Draw normals DF and EG on NOM from the points D and E respectively. Measure the length of the normals DF and EG. Find DF upon EG. This ratio is constant and it gives the refractive index of glass. This can be seen as follows. In right-angled triangle OFD, sine I is equal to DF upon OD. And in right-angled triangle OGE, sin R is equal to EG upon OE. Therefore, mu is equal to sin I upon sin R is equal to dF upon OD upon EG upon OE. But OD is equal to OE being the radii of the same circle. Therefore, mu is equal to dF upon EG. 9. Repeat the steps 3 to 8 of the experiment for different values of angle of incidence I equal to 50 degrees, 60 degrees, 70 degrees, 80 degrees, and in each case, find the ratio sin I upon sin R or dF upon EG. 10. Record your observations in a table shown below. Angle of incidence I, angle of reflection R, sin I, sin R, refractive index mu is equal to sin I upon sin R. When I is equal to 40, R is equal to 25.5, sin I is 0.643, sin R is 0.431, mu is 1.48. When I is equal to 50, R is equal to 31, sin I is 0.766, sin R is 0.515, refractive index mu is equal to 1.46. When I is equal to 60, R is equal to 35.5, sin I 0.866, sin R is 0.581, mu is 1.52. When I is equal to 70, R is equal to 38.5, sin I 0.939, sin R 0.622, and mu 1.50. When I is equal to 80, R is equal to 41, sin I is 0.985, sin R is 0.656, and mu is equal to 1.50. From the above observation table, we find that the ratio sin I upon sin R or dF upon EG comes out to be a constant for each value of angle I. This verifies the second law of refraction. The ratio so obtained is equal to the refractive index mu of glass, the material of the block. Thus, the refractive index mu of glass can be determined. Further, the incident ray AO, the normal NOM at the point of incidence O, and the refracted ray OB are in the plane of paper, that is, in the same plane. This verifies the first law of refraction. Refraction of light through a rectangular glass block. Figure shows a rectangular glass block PQRL. A light ray AO falls on the surface PQ. NOM is the normal to the surface PQ at the point of incidence O. At the surface PQ, the ray AO enters from air, rarer medium, to glass, denser medium, so it slows down and bends towards the normal NOM. It travels inside glass in a straight path along OB. At the surface RS, the ray OB suffers another refraction. N1BM1 is the normal to the surface RS at the point of incidence B. The ray OB now enters from glass, which is the denser medium, to air, the rarer medium. So it speeds up and bends away from the normal N1BM1. It travels along BC in air. The ray AO is called the incident ray, OB the refracted ray, and BC the emergent ray. The angle AON is the angle of incidence I. The angle BOM is the angle of refraction R, and the angle CBM1 is the angle of emergence E. Since refraction occurs at two parallel surfaces, PQ and RS, therefore, angle MOB is equal to angle N1BO, and by the principle of reversibility of the path of a light ray, angle E is equal to angle I. That is, the angle of emergence E is equal to the angle of incidence I. Thus, the emergent ray BC is parallel to the incident ray AO. Displacement. In figure, we observe that due to refraction of light at two parallel surfaces of a parallel-sided glass block, the angle of emergence is equal to the angle of incidence. So the emergent ray BC and the incident ray AO are parallel. That is, they are in the same direction. But they are not along the same line. The emergent ray is laterally displaced from the path of the incident ray. The path of the incident ray AO in absence of glass block has been shown in figure by the dotted line OD. The perpendicular distance XY is equal to X between the path of emergent ray BC and the direction of incident ray OD is called the lateral displacement. The lateral displacement X depends on, first, the thickness of block or medium, second, the angle of incidence, and third, the refractive index of glass, and therefore also on the wavelength of light used. First, dependence on the thickness of medium. More the thickness of the medium, more is the lateral displacement. Second, dependence on the angle of incidence. More the angle of incidence, more is the lateral displacement. Third, dependence on the refractive index. More the refractive index of the medium, more is the lateral displacement. Since refractive index increases with the decrease in wavelength of light, so the lateral displacement increases with the decrease in wavelength of light. That is, lateral displacement is more for the violet light than for the red light. Multiple images in a thick plain glass plate or thick mirror. If a pin or an illuminated object is placed in front of a thick plain glass plate or a thick mirror and is viewed obliquely, a number of images are seen. Out of these images, the second image is the brightest, while others are of decreasing brightness. LMNP represents a thick plain mirror, of which NP is the silvered surface. An illuminated object A is kept in front of it. Consider two rays, one falling normally on the mirror and the other AB falling obliquely on it. When the ray of light AB falls on the surface LM of the mirror, a small part of the light, nearly 4%, is reflected in the direction BP, forming a faint virtual image at A1, while a larger part of light, nearly 96%, is refracted along BB' inside the glass. The ray BB', which strikes at B' is now strongly reflected back by the silvered surface PN inside the glass as B'(C). This ray is then partially refracted along CQ in air and partially reflected along CC' within the glass. The refracted ray CQ forms the virtual image A2. The image A2 is the brightest image because it is due to the light suffering a strong first reflection at the silvered surface PN. The reflected ray CC' further suffers multiple reflections at C', D, D', and refractions at D, E, F, and so on, within the thickness of glass plate, giving rise to multiple virtual images A3, A4, A5, and so on, of gradually decreasing brightness. Note 1. In figure, due to drawing, the rays BP, CQ appear to be far separated from each other, but actually they enter the eye simultaneously. 2. A thick glass plate also behaves like a thick plane mirror. B. Refraction of light through a prism. Prism. A prism is a transparent medium bounded by 5 plane surfaces with a triangular cross-section. 2 opposite surfaces of prism are identical parallel triangles, while the other 3 surfaces are rectangular and inclined on each other. Figure shows a prism in which the opposite surfaces ABC and DEF are triangular. The principal section of prism is the triangle ABC. The angle BAC is the angle of prism, which is denoted by the letter A. The 2 rectangular surfaces ABED and ACFD, shown shaded, are polished, which acts as the refracting surfaces. The line AD is the refracting edge, and the rectangular surface BCFE is the base of the prism, which is usually grounded or made rough. Note 1. The 2 refracting surfaces of a prism are not parallel to each other, but they are inclined on each other, making an angle A called the angle of prism. 2. In ray diagrams, a prism is shown only by its principal section ABC. Of light through a glass prism. Figure shows the principal section ABC of a glass prism. The angle of prism is angle BAC is equal to A. A monochromatic ray of light, that is, a light ray of single color, OP, strikes the face AB of the prism at an angle of incidence I1. It suffers refraction from air, rarer medium, to glass, which is denser medium, at the face AB, so it bends towards the normal PN, making an angle of refraction R1, and travels along PQ inside the prism. Thus PQ is the refracted ray. The refracted ray PQ strikes the face AC of the prism at an angle of incidence R2. It suffers refraction from glass, denser medium, to air, rarer medium, at the face AC, so it bends away from the normal NQ and emerges out of the prism as QR at an angle of emergence I2. Thus QR is the emergent ray. Note, due to the principle of reversibility of path of a light ray, if a ray directed along RQ is considered as the incident ray, it will follow the path QPO. It means that for the incident ray RQ, the emergent ray will be PO. Thus in a prism, the ray of light suffers refraction at 2 inclined faces, AB and AC, of the prism. In each refraction, the ray bends towards the base of the prism. At the first face AB of the prism, the ray OP, instead of going along OPM, has bent at P along PQ, so suffers a deviation by an angle MPQ equal to delta 1. At the second face AC, the ray PQ has bent at Q along QR, which appears to be coming along MQR, so suffers a deviation by an angle MQP equal to delta 2. In the absence of the prism, the incident ray OP would have travelled along OPML. The emergent ray QR appears to be coming along MQR. Thus, the prism has produced a deviation by an angle LMQ which is the angle between the direction of incident ray, OP, produced forward, and the emergent ray, QR, produced backward. It is called the angle of deviation and is denoted by the Greek alphabet delta. In figure, angle LMQ is equal to angle MPQ plus angle MQP. Therefore, angle of deviation delta is equal to angle MPQ plus angle MQP is equal to delta 1 plus delta 2. Let this be equation first. Since angle MPN is equal to I1, angle of incidence, and angle MQN is equal to I2, angle of emergence, therefore, angle MPQ is equal to delta 1 is equal to I1 minus R1, and angle MQP is equal to delta 2 is equal to I2 minus R2. Therefore, from equation first, delta is equal to I1 minus R1 plus I2 minus R2, or delta is equal to I1 plus I2 minus R1 plus R2. Let this be equation 9. Also for the quadrilateral APNQ in figure, angle APN is equal to angle AQN is equal to 90 degrees. Therefore, angle PNQ plus angle PAQ is equal to 180 degrees. But angle PAQ is equal to A. Therefore, angle PNQ is equal to 180 degrees minus A. Let this be equation second. But in triangle PNQ, angle PNQ is equal to 180 degrees minus R1 plus R2. Let this be equation third. Therefore, from equations second and third, 180 degrees minus R1 plus R2 is equal to 180 degrees minus A, or R1 plus R2 is equal to A. Let this be equation 10. Hence, from equations 9 and 10, delta is equal to I1 plus I2 minus A, or I1 plus I2 is equal to A plus delta. Let this be equation 11. Note, in a prism, the refraction of light occurs at two inclined faces. So the emergent ray is not parallel to the incident ray, but it is deviated towards the base of prism. On the other hand, in a parallel-sided glass slab, the refraction of light occurs at two parallel faces. So the emergent ray is parallel to the incident ray with a lateral shift. Factors affecting the angle of deviation. The value of the angle of deviation, or the deviation produced by a prism, depends on the following four factors. 1. The angle of incidence, I. 2. The material of prism, that is, on refractive index. 3. The angle of prism, A. And 4. The color or wavelength of light used. 1. Dependence of angle of deviation on the angle of incidence, I delta graph. It is found experimentally that as the angle of incidence increases, first the angle of deviation decreases and reaches to a minimum value for a certain angle of incidence. This position of prism with respect to the incident ray at which the incident ray suffers minimum deviation is called the position of minimum deviation. By further increasing the angle of incidence, the angle of deviation is found to increase. Note, to get the graph showing the variation of angle of deviation, with the angle of incidence experimentally, the direction of incident ray is kept unchanged and the prism is rotated. On rotation of prism, the direction of normal at the face of prism changes, so the angle which the incident ray makes with the normal, that is the angle of incidence, changes. The variation in the angle of deviation, delta, with the angle of incidence, I, is shown graphically in the figure. The curve shown on the graph is called the I delta curve, in which the minimum angle of deviation is shown by delta minimum. To get the curve experimentally, usually the direction of incident is kept fixed and the prism is rotated to change the angle of incidence. It can be shown that in position of minimum deviation of prism, delta minimum, angle of incidence is equal to the angle of emergence, that is, I1 is equal to I2. Hence, R1 is equal to R2. From geometry in the figure, it can be shown that the ray QR is parallel to the base BC. Thus, in this position, minimum deviation, the refracted ray inside the prism travels parallel to its base if the prism is equilateral, or the principal section of prism for an isosceles triangle. Thus, in this position of minimum deviation, I1 is equal to I2, which is equal to I, and delta is equal to delta minimum. For a given prism and given color of light is unique. Then from equation 11, delta minimum is equal to 2I minus A. Let this be equation 12. For a given prism and given color of light, delta minimum is unique since only one horizontal line can be drawn parallel to I-axis at the lowest point of I delta curve, that is only for one value of angle of incidence I, the refracted ray inside the prism is parallel to its base at different angles of incidence. The figure shows the deviation of a light ray by an equilateral prism of glass whose refractive index is equal to 1.5 at different angles of incidence. The values of different angles can be calculated using equations 1, 2, and 3 with A equal to 60 degree. In figure A, angle of incidence I1 is equal to 70 degree. Angle of emergence I2 is equal to 33 degree. And angle of deviation delta is equal to 43 degree. In figure B, I1 is equal to 48 degree, I2 is equal to 48 degree, and delta is equal to 36 degree. While in figure C, I1 is equal to 30 degree, I2 is equal to 77 degree, and delta is equal to 47 degree. These angles are calculated using the following relations. For refraction at the first phase, mu is equal to sine I1 upon sine R1. R1 is obtained. For refraction at the second phase, 1 upon mu is equal to sine R2 upon sine I2. And R1 plus R2 is equal to A, so I2 is obtained. Thus delta is equal to I1 plus I2 minus A is obtained. From the ray diagrams shown in the figure, it can easily be inferred that delta has the least value in figure B, when the angle of incidence I1 is equal to 48 degrees. The refracted ray PQ is now parallel to the base BC of the prism, and in this condition, the angle of emergence I2 is also 48 degrees, equal to the angle of incidence I1. This represents the position of minimum deviation where delta minimum is equal to 2I minus A, which equals 2 into 48 degree minus 60 degree. So delta minimum is equal to 36 degree. Dependence of angle of deviation on the material of prism or refractive index. It is found that for a given angle of incidence, the prism with a higher refractive index, example flint glass, produces a greater deviation than the prism which has a lower refractive index, example crown glass. Dependence of angle of deviation on the angle of prism. It is found that the angle of deviation, delta, increases with the increase in the angle of prism, A. Dependence of angle of deviation on the material of prism or refractive index. It is found that for a given angle of incidence, the prism with a higher refractive index, example flint glass, produces a greater deviation than the prism which has a lower refractive index, example crown glass. Dependence of angle of deviation on the angle of prism. It is found that the angle of deviation, delta, increases with the increase in the angle of prism, A. 4. Dependence of angle of deviation on the color or wavelength of light. The refractive index of a given transparent medium is different for the light of different colors. It decreases with the increase in the wavelength of light. Thus, the refractive index of the material of a prism is maximum for the violet light and least for red light. Consequently, a given prism deviates the violet light most and the red light least. That is, delta violet is greater than delta red. C. Simple applications of refraction of light. Real and apparent depth. An object placed in a denser medium, when viewed from a rarer medium, appears to be at a depth lesser than its real depth. This is because of refraction of light. Consider a point, an object O, kept at the bottom of a transparent medium, say water or glass. PQ is the surface separating the medium from air. A ray of light, OA, from the object O is incident on the surface PQ normally, so it passes undeviated along the path A', as seen in the figure. The other ray, OB, starting from the object O, strikes the boundary surface PQ at B and suffers refraction. Since the ray travels from a denser medium, water or glass, to a rarer medium, air, so it bends away from the normal N-BN, drawn at the point of incidence B on the surface PQ, and travels along BC in air. When viewed by the eye, the ray BC appears to be coming from a point I, which is the virtual image of O obtained by producing A' and CB backward. Thus, any object, for example a coin, placed at O will appear at I, which is at a lesser depth. that is AI, than its actual depth, which is AO. The shift OI by which the object appears to be raised depends on, first, the refractive index of the medium, second, the thickness of the denser medium, and third, the color or wavelength of incident light. The shift increases with the increase in the refractive index of medium and also with the increase in the thickness of the denser medium. But the shift decreases with the increase in the wavelength of light used. In the figure for the incident ray OB, angle of incidence is equal to angle OBN dash and angle of refraction R is equal to angle CBN. Since AO and BN dash are parallel and OB is a transversal line, so angle AOB is equal to angle OBN dash, which is equal to I. Similarly, IA dash and BN are parallel and IC is the transversal line. So, angle BIA dash is equal to angle CBN, which is equal to R. Now in right angle triangle BAO, sin I is equal to BA upon OB. And in right angle triangle IAB, sin R is equal to BA upon IB. But by Snell's law, refractive index of medium water to air is sin I upon sin R, which is equal to refractive index of air with respect to denser medium, or refractive index of air with respect to denser medium is equal to sin I upon sin R, which is equal to BA upon OB upon BA upon IB, which equals IB upon OB, or refractive index of denser medium with respect to air is equal to 1 upon refractive index of air with respect to denser medium, which equals OB upon IB. Since the point B is very close to the point A, that is, the object is viewed from a point vertically above the object O, therefore, IB is equal to IA and OB is equal to OA. Hence, refractive index of denser medium with respect to air is equal to OA upon IA, which is equal to real depth upon apparent depth. Let this be equation 13, or apparent depth, which is equal to real depth upon refractive index. Let this be equation 14. Thus, shift OI is equal to real depth minus apparent depth, which equals real depth into 1 minus 1 upon refractive index. Let this be equation 15. Since mu V is greater than mu R dash, therefore, the shift is more for the violet light than for the red light in a given medium. Note, the point B is very close to the point A, and both the rays OA dash and BC enter the eye simultaneously. In figure, they have been shown separately for the sake of clarity of the ray diagram. The shift by which the object appears to be raised depends on 1. The refractive index of the medium, 2. The thickness of the denser medium, and 3. the color or wavelength of incident light. 1. Dependence of shift on the refractive index. Higher the refractive index of the medium, more is the shift. 2. Dependence of shift on the thickness of medium. Thicker the medium, more is the shift. 3. Dependence of wavelength or color of light. The shift decreases with the increase in the wavelength of light used, since mu v is greater than mu r. Therefore, the shift is more for the violet light than for the red light in a given medium. First, for glass, refractive index of glass with respect to air is equal to 3/2. Therefore, the thickness of glass slab appears only 2/3 of its real thickness when it is viewed from air by keeping the eye vertical above the slab. Second, for water, refractive index of water with respect to air is equal to 4/3. Therefore, the depth of water pond appears 3/4 of its real depth on seeing it from air in a nearly vertical direction. That is, it appears shallow. This is why a fish, when seen from air, appears to be nearer the surface of water than at its actual depth. Note, the apparent depth of an object lying in a denser medium is always less than its real depth when viewed from any direction in the rarer medium. But the above equations 13, 14, and 15 are valid only when the object is seen from vertically above. Bending of a stick underwater. The figure shows a straight stick or pencil XOP which is placed obliquely in water. The portion OP of the stick or pencil underwater appears to be shortened and raised up as OP dash. Why is this? Well, this is due to refraction of light in passing from water to air. The rays of light coming from the tip P of the stick or pencil when passing from the water to air bend away from the normal and appear to be coming from a point P dash, which is the virtual image of the point P. The same is true for every point of the stick or pencil inside the water. Thus, the part OP of the stick or the pencil appears to be at OP dash. That is, the immersed part of the stick appears to be raised and therefore bent at the point O on the surface of water, and the stick or pencil XOP appears as XOP dash. Note, an object placed in a rarer medium when viewed from a denser medium appears to be at a greater distance than its real distance. In figure, an object O placed in air when viewed from water appears to be at I, which is higher than the object O. Some consequences of refraction of light. In our daily life, we come across many phenomena which are caused by refraction of light. Some of these are given here. A star appears twinkling in the sky. The sun is seen a few minutes before it rises above the horizon in the morning, and in the evening, few minutes longer after it sets. A coin kept in a vessel and not visible when seen from just below the edge of the vessel can be viewed from the same position when water is poured into the vessel. A print appears to be raised when a glass block is placed over it. A piece of paper stuck at the bottom of a glass block appears to be raised when seen from above. A tank appears shallow than its actual depth. A person's legs appear to be short when standing in a tank. Critical angle and total internal reflection. Transmission of light from a denser medium, glass or water, to a rarer medium, air, at different angles of incidence. Consider the refraction of light from a denser medium to a rarer medium. When a light ray traveling in a denser medium falls on the surface separating it from a rarer medium, it is partly reflected back into the denser medium and partly refracted in the rarer medium. The refracted ray bends away from the normal on the surface at the point of incidence, obeying the laws of refraction. Now we shall consider this process of reflection and refraction at different angles of incidence. First, when the angle of incidence is small, I is less than C. In figure, a light ray AO traveling in glass is incident at the glass-air interface at a small angle of incidence I. It is partly reflected and partly refracted. We get a weak reflected ray OC and a strong refracted ray OB. Since the incident ray bends away from the normal when it suffers refraction from glass to air, therefore the angle of refraction R is greater than the angle of incidence I. Now, if the angle of incidence I is gradually increased, the angle of refraction R also increases, but the intensity of refracted ray keeps on decreasing. Finally, the angle of refraction reaches its maximum possible value equal to 90 degrees at a certain angle of incidence, I is equal to C. Here, C is called the critical angle. Second, when the angle of incidence is equal to the critical angle, I is equal to C. At angle of incidence equal to the critical angle, I is equal to C, the angle of refraction becomes 90 degrees, as shown in figure. The refracted ray is along the glass-air interface and it is very weak. In figure, for incident ray AO at I is equal to C, the refracted ray is OB and the reflected ray is OC. First, when the angle of incidence is small, I is less than C. In figure, a light ray AO traveling in glass is incident at the glass-air interface at a small angle of incidence I. It is partly reflected and partly refracted. We get a weak reflected ray OC and a strong refracted ray OB. Since the incident ray critical angle, we have read that when a ray of light passes from a denser medium to a rarer medium, at a certain angle of incidence, IC, the angle of refraction becomes 90 degrees. That is, at I is equal to IC, R is equal to 90 degrees. The angle is called the critical angle. Thus, we can define the critical angle as follows. Critical angle is the angle of incidence in the denser medium, corresponding which the angle of refraction in the rarer medium is 90 degrees. Relationship between critical angle and refractive index. In the figure, AO is an incident ray from glass to air at an angle of incidence I equal to C, which is a critical angle, for which the angle of refraction is 90 degrees. Therefore, the refractive index of air with respect to glass is equal to sine C upon sine 90 degrees. But sine 90 degrees is equal to 1. Therefore, refractive index of air with respect to glass is equal to sine C. But refractive index of glass with respect to air is equal to 1 upon refractive index of air with respect to glass. Therefore, refractive index of glass with respect to air is equal to 1 upon sine C, which equals cosec C. Let this be equation 16. Thus, knowing the refractive index of the denser medium with respect to the rarer medium, we can calculate the critical angle for that pair of media. Examples. First, for glass, refractive index of glass with respect to air is equal to 3 upon 2. Sine C is equal to 1 upon refractive index of glass with respect to air, which equals 2 upon 3, or C is equal to 42 degrees. Since sine 42 degrees is equal to 2 upon 3. Second, for water, refractive index for water with respect to air is equal to 4 upon 3. Sine C is equal to 1 upon refractive index for water with respect to air, which equals 3 upon 4, or C is equal to 49 degrees, since sine 49 degrees is equal to 3 upon 4. Hope it's all clear till now. Critical angle for some substances with respect to air. Angle for some substances with respect to air. Critical angle for some substances with respect to air. Water, turpentine, glass, flint glass, diamond. The table. Refractive index of water is 1.33 and its critical angle 48 degree, 45 minute, which is approximately equal to 49 degree. Refractive index of turpentine is 1.47 and its critical angle is 42 degree, 54 minutes, which is approximately equal to 43 degree. The refractive index of glass is 1.5 and its critical angle is 41 degree, 48 minute, which is approximately equal to 42 degree. The refractive index of flint glass is 1.57 and its critical angle 39 degrees, 28 minutes, which is approximately equal to 39 degree. And the refractive index of diamond is 2.41 and its critical angle is 24 degree, 30 minute, which is approximately equal to 25 degrees. This is affecting the critical angle. The critical angle for a given pair of media depends on their refractive indices. But the refractive index of a medium is affected by the following two factors. 1. The color or wavelength of light, and 2. The temperature. 1. Dependence on the color of light. The refractive index of a transparent medium decreases with the increase of wavelength of light. It is most for the violet light and least for the red light. Therefore, the critical angle for a pair of media is least for the violet light and most for the red light. That is, the critical angle increases with the increase in wavelength of light. 2. Dependence on temperature. On increasing the temperature of medium, its refractive index decreases, so the critical angle for the pair of media increases. Thus, critical angle increases with the increase in temperature. Internal reflection. When light travels from a rarer to a denser medium, at all angles of incidence, a part of it is reflected and the rest of it is refracted at the boundary surface. Thus, both the reflection and refraction occur simultaneously. On the other hand, when light travels from a denser to a rarer medium, under certain condition, when the angle of incidence is greater than the critical angle, no part of light is refracted, but the entire light is reflected back in the same medium. In figure, the light ray AO gets entirely reflected as OC, obeying the laws of reflection, and it does not suffer refraction. This phenomenon is called total internal reflection. Thus, when a ray of light traveling in a denser medium is incident at the surface of a rarer medium, at the angle of incidence greater than the critical angle for the pair of media, the ray is totally reflected back into the denser medium. This phenomenon is called total internal reflection. Initial conditions for the total internal reflection. There are the following two necessary conditions for the total internal reflection. 1. The light must travel from a denser to a rarer medium. 2. The angle of incidence must be greater than the critical angle for the pair of media. Note: in the process of total internal reflection, 100% energy or intensity of light is reflected back. No other device, such as plane mirror, etc., produces 100% reflection due to absorption and refraction of some part of light. Due to this property, the phenomenon of total internal reflection is used in the construction of periscope, binocular, and certain types of camera in which a total reflecting prism replaces a plane mirror for the reflection of light. And total internal reflection of light rays at different angles of incidence. Figure shows the refraction of light rays from a point source A kept in a denser medium to a rarer medium at different increasing angles of incidence. For the ray AO, the angle of incidence is 0. It is refracted as OA dash. For the ray AP, the angle of incidence is less than the critical angle C, that is, I less than C. It is partly reflected as PB and partly refracted as PC. For the ray AQ, the angle of incidence is equal to the critical angle for the pair of media. That is, I is equal to C. So it is partly reflected as QB dash and partly refracted as QC dash at the angle of refraction equal to 90 degrees. For the ray AR, the angle of incidence is greater than the critical angle. That is, I greater than C. So, it is totally reflected as RB double dash at an angle of reflection R is equal to I, and no refraction occurs. Note: the above phenomenon of refraction and total internal reflection can easily be demonstrated with the help of a laser pen source. The main precaution is taken that the laser source is not seen directly, as it may damage the eyes. Total internal reflection in a prism. Now we shall consider the phenomenon of total internal reflection in three different prisms. 1. 45 degrees, 90 degrees, 45 degrees prism, that is, right-angled isosceles prism or total reflecting prism. 2. Prism of each angle 60 degrees, that is, equilateral prism. And 3. 30 degrees, 90 degrees, 60 degrees prism, that is, a right-angled prism. 1. Total internal reflection through a 45 degrees, 90 degrees, 45 degrees prism, or right-angled isosceles prism. Total reflecting prism. A prism having an angle of 90 degrees between its two refracting surfaces and the other two angles each equal to 45 degrees is called a total reflecting prism because the light incident normally on any of its faces suffers total internal reflection inside the prism. Due to this behavior, a total reflecting prism is used for the following three purposes. A. To deviate a ray of light through 90 degrees. B. To deviate a ray of light through 180 degrees. And C. To erect the inverted image without producing deviation in its path. To deviate a ray of light through 90 degrees. In figure, ABC is a total reflecting prism. A beam of light is incident normally at the face AB. It passes undeviated into the prism and strikes at the face AC at an angle of incidence equal to 45 degrees. For glass-air interface, the critical angle is about 42 degrees. Therefore, the beam of light suffers total internal reflection at the face AC because the angle of incidence is greater than the critical angle. The reflected beam inside the prism then strikes the face BC, where it is incident normally, and therefore passes undeviated. As a result, the incident beam gets deviated through 90 degrees, emerging out through the prism. Figure shows the path of two rays PQ and P'(Q') through the prism and then out of it. Note, by the principle of reversibility of path of light, if light is incident normally on the face BC of the prism, it will emerge out from the face AB after suffering total internal reflection at the face AC. Use. This action of prism is used in a periscope where a total reflecting prism is preferred over a plane mirror. B. To deviate a ray of light through 180 degrees. In figure, the beam of light from the object PQ falls normally on the face AC, that is, hypotenuse of the prism, so it enters undeviated inside the prism and strikes the glass-air interface AB of the prism. Since the beam of light is traveling from glass to air at an angle of incidence equal to 45 degrees, which is greater than the critical angle, which is equal to 42 degrees for glass to air, therefore, the beam of light suffers total internal reflection. The reflected beam inside the prism strikes the face BC at an angle of incidence equal to 45 degrees, so it again suffers total internal reflection. The beam of light inside the prism now falls normally on the face AC and therefore passes undeviated out of the prism, forming the image P'(Q') of the object PQ. The beam thus gets deviated by 90 degrees at each reflection, and the total deviation due to two reflections becomes 180 degrees. Use. This action of prism is used in a binocular and camera to invert the image without the loss of intensity, to erect the inverted image without deviation. In figure, the beam of light from the object PQ is incident parallel to the face AC, that is hypotenuse of the prism, and strikes the face AB of the prism. It suffers refraction from air to glass and strikes the face AC of the prism, traveling from glass to air at an angle of incidence greater than the critical angle, which is equal to 42 degrees. Therefore, it suffers total internal reflection. The beam inside the prism now strikes the face BC at an angle of incidence less than the critical angle. Hence, it suffers refraction from glass to air and bends away from the normal. The beam emerges parallel to the face AC. As a result of refraction, on emergence, the rays are inverted, and for the inverted object PQ, the erect image P-Q- is obtained. A prism, when used in this manner, is called the erecting prism. Use: this action of prism is used in a slide projector. 2. Total internal reflection through a prism where each angle is 60 degrees, that is, equilateral prism. A prism of each angle 60 degrees can be used to deviate a light ray through 60 degrees by total internal reflection. Figure shows a prism ABC of each angle 60 degrees. A light ray PQ incident normally on the face AB of the prism passes undeviated as QR into the prism, and it strikes the face AC at an angle of incidence 60 degrees at the point R. Now the light ray QR suffers total internal reflection at the glass to air interface, since the angle of incidence, which is equal to 60 degrees, is greater than the critical angle, which is 42 degrees, such that the angle QRS is 120 degrees. The ray RS obtained after total internal reflection falls normally on the face BC of the prism, and so it passes out undeviated through the face BC. Thus, ST is the emergent ray. From figure, it is clear that the incident ray PQ has turned through an angle of 60 degrees towards the base from its initial direction, and it emerges out as external reflection and refraction of light through a 30 degrees, 90 degrees, 60 degrees prism, or right-angled prism. A 30 degrees, 90 degrees, 60 degrees prism can be used to deviate a light ray through an angle less than 60 degrees by total internal reflection. Figure shows a prism ABC of angles 30 degree, 90 degree, and 60 degree. A light ray PQ incident normally on the face BC of the prism, opposite to the refracting angle 30 degrees, passes undeviated as QR into the prism, and it strikes the face AC at an angle of incidence 60 degrees at the point R. Now the light ray QR suffers total internal reflection at the glass-air interface, since the angle of incidence, which is equal to 60 degrees, is greater than the critical angle, which is 42 degrees. The ray RS obtained after total internal reflection is incident at the face AB of the prism at an angle of incidence equal to 30 degrees. This angle of incidence at glass-air interface is less than the critical angle, so the ray RS is refracted from glass to air as ST with an angle of refraction greater than 30 degrees. Non-occurrence of total internal reflection through a 30 degree, 90 degree, 60 degree prism. In figure A, a light ray PQ is incident normally on the face AB of the prism ABC, while in figure B, a light ray PQ is incident on a part of face AC of the prism ABC. In both the cases, the light ray does not suffer total internal reflection inside the prism and gets refracted as RS, obeying the laws of refraction. In each case, the angle of incidence at the other face inside the prism is 30 degrees, which is less than the critical angle. A ray of light incident normally on hypotenuse of prism below the foot of perpendicular on it from its opposite corner suffers total internal reflection and gets deviated by an angle greater than 60 degrees. In figure, a light ray PQ is incident normally on the face AC, hypotenuse of the prism, in the portion DC, such that the point D is the foot of perpendicular from B on AC. It passes undeviated as QR inside the prism and strikes the face BC of the prism at an angle of incidence 60 degrees, which is greater than the critical angle, which is equal to 42 degrees. The ray suffers total internal reflection inside the prism as RS. The reflected ray RS then strikes the face AB at an angle of incidence 30 degrees. So it suffers refraction from glass to air and emerges out of the prism as ST, bending away from the normal at the face AB. Thus, the incident ray PQ gets deviated through an angle greater than 60 degrees. Of a total internal reflecting prism in place of a plane mirror. A total reflecting prism is used in place of a plane mirror to deviate the light ray by 90 degrees in a periscope and by 180 degrees in a binocular as well as in a camera. The reason is that due to total internal reflection in the prism, the entire incident light, 100%, is reflected back into the denser medium, whereas in ordinary reflection from a plane mirror, some light is refracted and absorbed, so the reflection is not 100%. Thus, the image obtained by the use of a total reflecting prism is much brighter than that obtained by using a plane mirror. Further, the brightness of image formed by a total reflecting prism always remains unchanged, while due to deterioration of silvering of the plane mirror after a long use, the image formed by it becomes faint. Distinction between the total internal reflection and reflection from a plane mirror. 1. Total internal reflection takes place only when light passes from a denser medium to a rarer medium at an angle of incidence greater than the critical angle for that pair of media. While reflection from a plane mirror takes place when light is incident on a plane mirror from any medium at any angle of incidence. 2. In total internal reflection, the entire light is reflected, while in reflection from a plane mirror, only a part of light is reflected, while rest is refracted and absorbed. In total internal reflection, there is no loss of energy. The energy of the reflected ray is same as that of incident ray. Whereas, in reflection from a plane mirror, there is a loss of energy. The energy of reflected ray is less than that of the incident ray. In total internal reflection, the image is much brighter and the brightness remains unchanged even after the long use of the total reflecting device. Whereas, in reflection from a plane mirror, the image is less bright and the brightness gradually decreases as the silvering on mirror becomes old and rough. Some consequences of total internal reflection. In our daily life, we observe many consequences of total internal reflection. Some of these are given below. 1. On a hot sunny day, a driver may see a pool of water or wet road in front of him at some distance. It is the phenomenon of mirage which is often observed in desert. 2. An empty test tube placed in water in a beaker with mouth outside the water surface shines like a mirror when seen at certain angles. 3. A crack in a glass vessel often shines like a mirror. 4. A piece of diamond sparkles when viewed from certain directions. 5. An optical fiber is used to transmit a light signal over a long distance without any loss of energy.